So as you remember, before the storm, we had 2 days where we were trying to basically build a Allen key filter that would implement a pair of complex conjugate poles at a location of our choosing. So we did a derivation of that, and then in my fear that nobody understood the derivation, I actually created a document where I did the entire derivation and tried to spell it out and posted that document to Blackboard so that everybody would understand it. Did everybody get a chance to look at that and download it? Some of you did. Did you know that I have a button on Blackboard that lets me know who's looked at what? Yes, it's true. So I put in a lot of effort writing this thing where so you can understand, so everybody can have accurate, complete notes on how to derive the Allen key filter, how we came about choosing our poles, how we built the Allen key filter resistor and capacitors to get those poles exactly where we wanted. Okay, no one's some of you have looked at it. I know exactly who's looked at it. I know what days you looked at it. Yes, sir.
So we have no power, no internet to look at it.
I'm just saying. I know all. That's all I'm saying. I'm not saying there weren't good excuses. I'm just saying it was up since Friday. So, please read it. I don't really intend to burn more lecture time on it because I feel like to the extent that I was going to make a point, the point has been made. But, there are 2 PDFs that I've posted to Blackboard. Please read them. I think they're helpful. I put a good deal of effort into making them look nice and readable and so on. And if you have questions, I expect that you'll be contacting me. All right? Thank you. Okay, next item of business. You had a homework assignment that was due today? Okay, did that go okay? No, yes, sir.
I have no power.
You have no power, no internet. Okay, well, we can take that up after class. But you have like a whole 10 days to work on it, no? All right, we'll figure something out. But whatever, that's due today. The other thing is, a week from Friday, you have a test. And hopefully by Friday, by next lecture, I will release to you a list of topics, a list of study questions, so on and so forth. But we're getting to the point now where we need to demonstrate that we understood the concepts of filtering, first-order filtering, second-order filtering, low pass, high pass. If I give you a transfer function, you can tell me the magnitude and phase response to a particular frequency, so on and so forth. You should be reasonably comfortable with the mechanics of filtering. So, like I said, on Friday, I'll give you a list of topics, and we'll have a test in 9 days. Okay? I've been mindful to try to spread the exams out this semester and not to get them all bunched up, when everybody else is having their exams, or to have them like all bunched up close to the end of the semester. So I've tried to spread them out so we can attack our material like a little bit at a time as opposed to having like a monster test or something. So I don't know. It doesn't seem like that long since we've had an exam, but I'm hoping that that's actually a good thing, not a bad thing. All right, questions? All right, we're going to start chapter 9, believe it or not. And chapter 9 is about power. So we are going to talk about some concepts of power and kind of like how they relate to some circuit design stuff. And yes. What is the test on? Okay, so on Friday, I'm going to give a list of topics, and those will be the topics you'll have to study. I'll tell you that on Friday. Okay. So we're going to start chapter 9. You should start reading chapter 9. To the extent that we were sort of going rogue and not working out of the book, that's over now. I'm sort of back to kind of hugging pretty closely what the book is doing. So we'll be discussing power. All right, that's sort of our next couple weeks game plan. So the good news is the math is actually, I think, a little bit less ridiculous than some of the stuff we've been dealing with in the past. So let me start with this. So let me have a DC source here. let's call this resistor R. And let's say there's another resistor here. So let's call this R1 and R2. So I think you may have done this in a previous class, but can you pick resistor 2 to maximize power? So pick a value for resistor 2 to maximize power to that resistor. Does everybody remember the formula for power? IV, right? It's voltage times current. So I want you to see there's kind of a trade-off here. If I make that, okay, and so it's P equals IV, and for a resistive circuit, there's two other shortcuts that we can use to write this, isn't there? We can either say I squared over R, or we can say V squared R, because V equals IR. Nope, did I get it backwards? Oh, so close. We know that V equals IR. Right, so it's either I squared R, or it's V squared over R. That's just when your load is a resistor. So here's the interesting thing. If I make my resistor, if I make R2 bigger, I get a bigger voltage. If I make R2 bigger, let's say we call this V out. If I make R2 bigger, what happens to V out? Is it bigger or smaller? Gets bigger, because it's a voltage divider. If I make R2 bigger, that means V out gets bigger. Okay, so that would seem to indicate that the power gets bigger. But at the same token, if R gets bigger, what happens to the current? Smaller. Okay, so if I make R bigger, voltage gets bigger, but current gets smaller. And conversely, if I make R smaller, current gets bigger, but voltage gets smaller. So clearly, there's got to be some sweet spot in the middle where I'm maximizing both voltage and current. So can we think of a way that we can pick R2 in order to maximize the power that's dissipated through it? Okay, and the reason we're doing this is just so that we can kind of wrap our heads around a fairly straightforward example before the examples get uglier once we put capacitors in there for our load. But this basically already is a Thevenin, right? Right, but I want to know why they equal to each other. Like, what's the math that we could actually do? Like, if I want to maximize power, what could I do? How do we maximize things mathematically? Calculus? How do we optimize things in calculus? Take a derivative. I'll pretend you said take a derivative. Did you say take a derivative? It doesn't matter. Okay. Right. Remember, when we want to optimize things mathematically, what we do is we take a derivative and set it equal to 0. And that tells you where it peaks, right? So what if we were to plot power as a function of resistance? Okay. So just for a sanity check, if R2 equaled 0, how much power would be dissipated through R2? Yeah, if R2 was 0, how much power would be dissipated through it? 0. If R was 0, there would be no power going through that resistor. Okay, so if R2 is 0, there's no power because there'd be no voltage across it. What about if R2 is infinity? Would there be any power going through R2? Yeah? How much current, if R2 is infinity, how much current would be going through it? 0. And can you have any power without current? No, you cannot. So if R2 is infinite, you'd also have 0 power. So somewhere in the middle, so presumably, if we were to connect the dots, power as a function of load resistor is going to look like that. And I want to know what value of R2 is going to maximize my power. So what I'm going to do is, I'm going to, how can I do this? I'm going to close that door. That's what we'll start by doing. So how can I figure out how to maximize this? Yeah, take derivative of power with respect to the resistor. Okay, I'm down with that. So let's keep in mind that we need to write an expression for power in terms of just the source voltage. Okay, so let's call this V source and V load. I want to write an expression for power that's only in terms of my source voltage and R1 and R2. Yes?
You're like looking for a critical point?
Yeah, that's exactly what we're looking for. Right, and the critical point will be where that derivative equals 0. Okay, so let's see. Power, the power through R2 is going to be equal to the voltage across R2, which is what? R2, it's a voltage divider, right? Times V supply. Okay, so that's the voltage divider. That tells me the voltage across R2, the voltage across my load. Okay, so is power just equal to voltage? No, it's equal to voltage times current. So what's the expression for the current? Vs, voltage over R1 plus R2. So that's the expression for power. Oh boy. Okay. And I want to maximize this, right? I want to find the maximum of this power. So essentially what I want to do is I want to take the derivative of power with respect to R2 and figure out how to maximize it. Oh boy. Okay. Any thoughts? We got a mess on our hands, don't we? Can we think our way through this? Can we intuit our way through this? I'm serious. All right. Well, let's just do the derivative. So if I clean this up a little bit, I've got R2 Vs squared over R1 plus R2 squared. I'm going to take the derivative of that with respect to R2. Does everybody understand why I'm taking that derivative? So I'm trying to optimize power. And the way we optimize anything is to take its derivative and set it equal to 0. That's what we learned in calculus class. So how am I going to work this nonsense? I got to take its derivative. Vs squared is a constant, right? So that we don't really care about that. I'm going to make this a little easier. I don't know about you, I can never remember the quotient rule. But what I can remember is the product rule. How about that? Is that better? Instead of dividing it by r1 plus r2 squared, I'll multiply it by r1 plus r2 to the negative 2. Okay, so I'm going to take the derivative of that with respect to r2. So I get vs squared r1 plus r2 to the negative 2. So that's what I get from taking the derivative of that term. So remember the product rule? It's derivative of this term times that plus that times the derivative of that term. Okay, so I've done the derivative of the r2. Now I've got to do the derivative of that term. So it's going to be minus 2 r2 v supply squared r1 plus r2 to the minus 3 power. And can I stop? Or do I need to keep going?
It should be multiplied by an r1 too.
Why?
Because you have to take the derivative of the inside of the parentheses, right?
Right, but I take the derivative of the inside of the parentheses with respect to r2, I just get 1. So I should be done. So I take this whole mess, set it equal to 0. Okay, this is actually not going to be so bad. Vs hits the road, and that should be obvious, right? It doesn't matter what my Vs is. That's not going to affect my ability to optimize this. Okay, so the Vs's divide out. That's nice, right? We should be grateful for that. What else can I do?
R1 plus R2.
Right, I'm also going to multiply through by r1 plus r2 cubed. All right, look what's going to happen. If I take this term and multiply it by r1 plus r2 cubed, it turns into r1 plus r2 minus 2r2, and if I take this term and multiply it by r1 plus r2 cubed, it just goes away, equals, oh boy, we're getting somewhere. What am I solving for again? R2. Okay, so what's my value of R2 that's going to make this happen? R2 equals you did it. I'm proud of you. Okay, so to answer a challenging question, how do we maximize the power delivered to the load? The answer is you make your load resistance the same as your source resistance. All right? So let's do one more thing. So we know that this is going to be equal to R1. We know that the value of R2 that maximizes your power delivered to the load is to make your load equal to R1. What is the actual value of that power? Can we calculate what that actual maximum power is? Sure we can. We just take this equation and we substitute in what? Yeah, you just see everywhere you look for R2 and you say we've decided to maximize power, we've decided to make R2 equal to R1. So you just let R2 equal to R1. So you'll have R1, 2R1, 2R1. So the denominator is 4R1 squared. That's an R1 now. So that's V squared over 4R1. Is that right? Did I screw that up? It should be V squared R1 over 2R1 squared. So that'll be V squared over 4R1. So it's your V supply squared over 4R1. Good. So we're going to play this game, right? This is a thing that electrical engineers worry about all the time, right? So suppose you've got, so any electrical circuit, and I mean basically any electrical circuit, you can always think of it like this. So somebody was saying before about Thevenin, and Thevenin is totally right on the button, actually. So let's say you've got some sophisticated circuit. All right? It's got all sorts of squiggles and God knows what and all sorts of things, okay? But the whole point of that circuit is to deliver some sort of power to a load. All right? So you could think about something as simple as like a light switch. All right? Like why do your light bulbs have light bulbs are designed with an impedance inside of them, right? They have a resistance. There's a little, I guess for an incandescent light bulb, it's got a little coil in there, and that coil heats up. But it's a wire, right? It's got resistance. Why does it have the resistance that it has? Right? Why not smaller? Why not bigger? Well, somebody's figured out that if you've got this power station and this home wiring circuitry nonsense in your house, you might as well design the light bulb to maximize the amount of power that's delivered to the light bulb. And it turns out that in order to maximize that power that's delivered to the source, you have to be picky about the resistance of your load. Okay? So this is what this is the name of the game. This is basically what's going to eat up the next, basically till the exam in terms of trying to conceptualize this. What we're going to be trying to do is to figure out how to design a load to get the most out of the circuit. So you say, oh, well, my circuit, you just did an easy example, right, where you just had a resistor. What if it was more complicated than that? And I say, no problem. That's why you learn to take Norton and Thevenin equivalents. So what you could always do is, no matter how sophisticated your circuit is, you could always redraw it as a Thevenin equivalent voltage source and a Thevenin equivalent impedance, right? In circuits 1, this would have always been a resistor. But now that we're in circuits 2 and we're more sophisticated and worldly, we understand that a Thevenin impedance could just as easily contain complex components as well. It's just a little extra math, but it's, conceptually it's all the same. It's an open circuit voltage, gives you V Thevenin, and then the, you short it. No, am I getting those backwards? The Thevenin impedance is, if you look at into your circuit with the leads open, that's your open circuit voltage. And then if you short the leads, that gives you your short circuit current. And if you take the ratio, that gives you the Thevenin impedance. I still remember. Okay, good. It's been a while. So circuits are always built this way. No matter how sophisticated your circuit is, you can conceptualize it as a source and a Thevenin source impedance. And then you're going to deliver that source impedance to what we call the load. Okay, and we've talked about the load before. All right? And the name of the game is maximizing power to the load. Good. So what we've just discovered is that if V Thevenin is a DC source, and if the source impedance is purely resistive, then the load impedance that maximizes power transfer is also the same resistance as the source. Okay? That maximizes power. That maxes power to load. Which is a good thing. What happens if we don't maximize power to load? Who cares? Why should we care about maximizing power to load? It's the most efficient, right? We waste the least amount of power. That's exactly right. It's the most efficient, the least wasteful way of delivering power to our load. This is pretty cool. If I plotted this, do you think I would get that? You should, right? At very low, well, watch this. I came to erase this and I noticed it and I thought I'd point it out before I erased it because it's kind of cool, right? So engineers are good at these sort of hand-waving games. So watch this. If R2 is real small, then this equation, if R2 is real small, then you can sort of ignore the R2s in the denominator because they're going to be a lot smaller than R1. And what are you left with? You're basically left with Vs squared over R1 squared, which is a constant, times R2. So at low values of R2, you've basically got a linear increase. Yeah? Then at high frequencies of R2, not high frequencies, listen to me. For high values of R2, you can basically, if R2 is so big that you can basically ignore R1, so now your denominator becomes R2 squared. Your numerator has an R2 in it, so those cancel. You're just left with Vs squared over R2. And we all know that when you have something over, like 1 over R2 would look like that. So for low R2s, you have a linear, sort of a linear-ish increase. For high R2s, you have a decrease. And then somewhere in the middle is the sweet spot. And we've happened to discover that that sweet spot is the same as happens when your load is the same as your source. Okay, that wasn't so bad. Should we make it bad? Let's do it. All right. Well, as you may have noticed, everything we're doing this semester, or all the fun stuff we're doing this semester, has to do with AC sources, right? Alternating current sources. So what I want to know is what happens now if I change this from being a DC source to an AC source? Now what happens? Now we have a mess on our hands. So what we're going to do is this. Today we're going to play a game called Calculating. Oh, I have to remember we have a quiz, so I got to make sure I leave time for the quiz, just to give you something to think about. So let's see, 10. Okay, well, you know, we'll get there in our sweet time. Come on back in. It's cool. Oh, it's locked? Should I charge him? $5. He thinks I'm kidding. Okay. Just PayPal me. All right. So what I want to know is how can we calculate power if this is an AC source? So let's start with making that an AC source, and we're going to do the same example with. Let's just start by making everything a resistor right now. Okay. I think we can come back on Friday and make it a bit more interesting by starting to introduce capacitors and inductors. But for right now, let's do the same example as before, but let's just introduce the headache that our source is an AC source. Okay, so let's say that V supply is equal to let's say V supply cosine omega t. Can you live with that? So here's my supply. It's got some magnitude cosine omega t. And I want to find the power through my load. So I need to know two things. I need to know the voltage across my load, and I need to know the current through my load. Yes, sir?
Why does your VS have weird things on top?
Just to make it look different than that one. It's like a capital VS. It's more impressive. My little serifs. There's nothing. It's just to make it look different. Just to differentiate it from that one. Okay. So what is the voltage going across my resistor? Yeah, it's going to be Vs R. It's a voltage divider, right? Okay, so R over 2R. Is that 1/2? R over 2R cosine omega t. Is that the power? Is that the voltage through the resistor? Yeah. There's no phasors involved here, right? Because there's no I don't have capacitors or inductors or anything to add phase to this. Everything's just reactive, so it's nice. So that's the voltage. That's the voltage through the load. What's the current through the load? Hey, these R's cancel, don't they? Look at that. Okay, that's nice. That's real nice. What's my current through the load? I'll give you a hint, it's not hard. Thank you. The current through the load is going to be Vs over 2R. The constant Vs over 2R? Cosine, right? Same frequency. Cosine omega t. So that's the current through the load. Yes, sir? What's that?
Both are canceled.
That was in the top. That was for the voltage. This was the voltage divider to give me the voltage across the load resistor.
Okay. It looks like you crossed out both R's.
I did cross out both R's. They canceled. It was the voltage divider, R over 2R,
Oh, okay.
and then they canceled. Okay. So that's voltage through load, current through load. How do I get power through load? Multiply them. So if I multiply them, so it's going to be voltage times current. All right, let's see if I can take a swing at this. So it's going to be V squared over 4 R. Am I good? Cosine squared omega t. Whew. I need a break. That was tough. Okay. Now, what? Okay. What do I do with this? What's happening to my power? Is it like before? When everything was DC, I had the same power. Like power was constant, right? What was it we got? We got like that maximum power. It was V squared over 4R. It never changed. Now look at my power as a function of time. What's my power doing? It's oscillating. From between what and what? What's the biggest power I ever get? Right, the biggest value that takes is Vs squared over 4R. And the lowest value it takes? Negative. Can't get negative. Cosine squared is a positive term, right? That smallest cosine square can be is 0. So this is basically going to look something like this. Except not as pretty as that. Okay, I lack certain artistic skills. So that's going to be Vs squared over 4R. All right. So there we go. So roughly it's going to look something like that. Now, here's the deal. The deal is that as engineers, this statement is 100% true, right? I've not lied to you in writing this equation down, right? This is totally correct. It's just not all that useful, okay? It's correct, it's just not useful because it's got this cosine term, and I think you can appreciate that the power, the intensity of the power really varies, you know, the frequency has a role, and it's just, it's not really helpful to express it that way. So instead what we're going to do is we're going to come up with a different method of expressing power. Okay, and that's where we'll at least set this up, and hopefully, we'll get as far as we can. So instead of expressing power as I have over there, which is correct, I want to emphasize that. That expression of power is correct for my circuit. That will tell me the power through my load is a function of time. But instead what I want to do is I want to express an average power per period. So in other words, what I'm going to do is I'm going to say, yeah. Whatever. This is a plot of power. What I really want to do is I want to say, okay, this power is periodic. So I'm going to look at one period, and I'm going to calculate the average power over that period. I mean, sometimes it was high, sometimes it was low, but I think we can all agree is that over that period, there must be some average value, which is the same as saying, if I were to integrate this over one period, that would give me some area, right? What I want to know is, what's the average power? What's the number that would give me this, like that if I did this integral, that would give me the same as the integral of the average, the integral of the cosine. That's what we call the average power. So once the area under the curve over one period and the area under this line under the period, once they have the same value, this becomes the average power. Are we all okay on that concept? If you get nothing other than the concept today, we'll do the math on Friday. Okay? So in other words, instead of thinking about power as being something that varies with respect to time, I mean, of course it does, but just to come up with a metric, like in order to have a number to communicate with each other, what we're going to do is we're going to talk about the average power. So to get the average power, we're going to find a number such that if you took that number and integrated it over one period, that would be the same thing. That's the average power. That's the same as the integral of the power curve over that same set of time. That's the definition of average power. What do you think? Is that a reasonable explanation of what average power is? So how can we figure that out? What is the average power? Can I at least set up the integral and then come back and solve it on Friday? What would I need to write? So I'm integrating. What am I integrating? 0 to, well, let's start with the function, then we'll deal with the limits of integration. What is the thing that I'm actually integrating? Am I integrating this curve? Okay, that's the average power. So I'm going to integrate my average power from what to what? 0 to 0 to what? One period? What is one period? I don't want to add another variable. Can I express a period in terms of some number that's already on the board? 2 pi over omega. Right? For any periodic signal, the period is always 2 pi over omega. The sooner you get to this, the sooner I give you your quiz, the more time you get for your quiz. So let's all be motivated. Okay, so that gives me the area under the curve. I need to do one more thing in order to get my average power. Divide by Yeah, divide by the period, right? Divide by the period. So I added another variable, even though I said I wasn't going to. Okay, where t is, right? If I divide by the period, that will give me the average power over one period. So, on Friday, we will examine a shortcut for doing this integral. Because it's not a really pleasant integral to do, right? And friends don't let friends do unpleasant integrals unless absolutely necessary. But what I care is that you understand conceptually what it is that we're trying to accomplish, okay? What we're trying to accomplish is the average power over one period. Okay? So, first we'll calculate average power over one period, then we'll try to maximize it, right? Then we'll start to talk about how to choose impedances to maximize average power over one period. Okay. Enjoy your